Grant?
Differential equations.
Okay.
Okay? And the first one is just like ridiculously long.
Okay.
There's like 7.
There's two
I'll see
ways.
what I can do.
There's two ways we can do it. You can verbalize these, or if you want to take a quick picture and send it to my email, I'll bring it up on the screen. Would that be easier? I'm probably going to have to write it out even if you did it the other way. So why don't you just verbalize it?
Okay. Yeah, that would probably be easier for me too.
Okay.
So the rate at which a population of bears in a national forest grows is proportional to 600 minus b of t.
Right. Just hold on a second. Let me think about it for a second. The rate, this is the, all right, go ahead and say it again. Let me see if I can write it out. The rate. Go ahead.
A population of bears in a national forest grows is proportional to 600 minus b of t.
600 of what?
600 minus b of t.
B of t being the population of the bears?
Yes. Well, here it says, where t is the time in years and b of t is the number of bears.
Okay. So the rate of growth, right, of the population is proportional. Is there parentheses, or are they just giving it to you as a word problem like that?
No, they're just giving it to me as a word problem.
Okay.
And then it says, at t equals 0, there are 200 bears in the forest.
So I should write that, b of 0 is 200.
Okay.
Okay. Differential equations always have two differentials in them. You never have just one differential. It doesn't make sense to say dp equals 10. Okay? In other words, you can't have one differential without another one.
Okay.
Now, the way you solve these problems is by separating the differentials, get all your p's on one side, all your t's on the other.
Right.
Let me think about that. Okay, so we're going to end up with, if I do that, let's see, we've got dp over k equals 600 minus b of t times, or dt. Okay, you with me?
Yep.
Now I want to integrate both sides.
Right.
Well, I can integrate that side. I can integrate that side. What's the integral of the left side?
It's just k to the -1, right?
Well, it's natural.
Oh no, it's
the natural log of
k. Sorry, my bad. I always forget which one.
It's all right. In other words, the derivative of, excuse me, I'm wrong. K is not a variable. K is a constant. So it's P over K. In other words, if it was just the derivative of dP, that's P. I mean the integral. The antiderivative of dP is P.
Right.
Because it's a 1 there. It turns into the variable. And the K I can take outside the integral sign because it's a constant. So I end up with P over K.
Okay.
Derivative of the integral of the left. The integral of the right is what?
Okay, so it'd be 600 squared over 2.
No,
Or wait, no, it
in other
would
words,
just be 600x.
a
Oh, sorry.
600t.
Yeah. And then
T.
it would be bt squared over 2.
Mm,
Or no, do I have to do like some sort of chain rule or something?
well, it depends on what b of t is.
Hmm. Is there any like other stuff you need to know?
Seems like they've left out some information here. Well, read the question again from start to finish.
Okay, the rate at which a population of bears in a national forest grows is proportional to 600 minus b of t, where t is the time in years and b of t is the number of bears. At time t equals 0, there are 200 bears in the forest. The rate of change of the population of bears is modeled by the differential equation db over dt is equal to 600 minus b of t. Oh wait, no, sorry. It's db over dt equals 600 minus b, and y equals b of t is the solution to the differential equation with the initial condition b of 0 equals 200. It's just like really wordy. I don't.
If we knew what this function was, then we could integrate.
Right. Because we can't have more than one variable, right?
Well, and apparently we don't need this k here either. I'm thinking for a moment here. T is going to be 600t minus the integral of b of t, whatever that is, dt, plus a c. And the c is critical because the initial condition allows you to solve for c. In other words, we know that b of 0 is 200.
Right.
So when I substitute 0 for t, I'm going to be able to solve for c. Once I solve for c, now I know my full formula. But there's... it's unfortunate that this is such a hard one to start with. Do you have any easy ones to start with? Because the concept of solving a differential equation is not that hard, but this one is particularly hard.
Okay. All right.
I'm not... it's been so long since I've handled these population questions.
Okay.
These are particularly kind of logistic functions almost.
Okay.
And it may be a logistic function because usually when you're dealing with populations in a park, you do have an upper limit on the growth. In other words, it's not going to expand exponentially forever. The bears are going to reach a point where there's a limited amount of resources and they're going to flatten off.
Right.
And I suspect that 600 is what that is. That's the upper limit of the bears population.
Yeah, I have an easier one though if you want to do that.
Let's start with an easy one, and at least I can explain the technique as to how to solve it, and then maybe we can back up and figure out what to do on that one, although it still seems like I'm missing something about that one.
Okay. All right.
You want me to find any? I could find a real easy one.
No, I have one. I can read it to you right now if you want. So consider the differential equation dy over dx is equal to xy cubed.
Yeah, something like this. These are
and then if it says find the particular solution to the differential equation with the initial condition of f of 2 equals -1.
Okay. Yeah, this is an easy one. We're still going to employ the same technique. We're going to separate the variables. We're going to get all the y's and the dy on one side, all the x's and the dx's on the other. And they have to be multiplied. They can't be being added, just for your information. So we end up with dy over y cubed equals...
Wait, are you like writing this down on the screen right now?
Oh, I am. Can you not see it?
No, I can.
Really?
I'm just left with the last image you had up.
Wow.
There we go. Sorry, that's better now.
It's just slow, it looks like.
Huh.
Can you see my bottom line here? dy over y cubed equals x dx?
Yeah.
Okay. Well,
Yeah.
I'll try to... I'm not sure what's going on. Maybe we just have a slow internet thing here.
Okay.
The next thing to do is to integrate both sides. Okay.
Okay.
And we have the functions here, so this is relatively... What's the integral of y to the minus 3?
Wait, why the minus 3? Do you move it up to the top now? I don't really understand.
Well, first of all, let's rewrite it.
Okay.
Since it was in the denominator, it's the same as y to the minus 3. That's the same as 1 over y cubed.
Okay.
And now,
I just got confused because the last one you did a natural log.
Using the power rule, always begin with the exponent, add 1 to the exponent, and divide by the new exponent. So if I add 1 to the exponent, it becomes that. If I divide by the new exponent, it becomes that.
Right. Okay.
That's the antiderivative of y to the minus third. On the right side, we have x squared over 2 plus c.
Okay.
Okay. Now, we need to solve for y. Once we solve for y and put in this initial condition, we're going to be able to solve for c.
Okay.
Okay, so let's solve for y. So what do we have here? We have 1 over minus 2y squared equals x squared over 2 plus c. So, now let's start out by multiplying everything by negative 2. So we get 1 over y squared equals negative x squared minus 2c.
Okay.
Which means y squared equals 1 over minus x squared minus 2c. Which means y is equal to plus or minus the square root of that. So now we have our f of x.
Okay.
Okay, that's f of x. Same thing as y. And now we know that the initial condition says f of 2 equals minus 1.
Mm-hmm.
So you see where I'm going to be able to solve for c.
Yep.
So let's see. If f of 2 equals minus 1, then minus 1 equals plus or minus the square root of 1 over x was what? 2?
Yeah.
So that's minus 4 minus 2c. Okay. So if minus 1 is equal, and this is your easy one. In other words, if minus 1 equals this, I can eliminate the plus sign, right? It's got to be the minus part.
Yeah. Mm-hmm.
So how do I solve this? If minus 1 equals this whole thing...
Well, you'd have to square both sides, right?
Yeah, or I could just eliminate the minuses immediately. So now I have 1 equals everything over there. So if I square both sides, I get this. And now solving for c gives me minus 4 minus 2c equals 1. Minus 2c equals 5. C equals minus 5 halves.
Okay.
And now we know our equation. In other words, C is minus 5 halves. and it's negative.
Cool.
I'll plug in 5 halves or minus 5 halves, and there's your answer for what the function is.
Okay.
It might even be given like that. They probably reduced that a little bit. They changed that to a plus sign, crossed out the 2's, and you'd have minus x squared plus 5 in the denominator. Okay?
All right.
So that's the basic strategy when you're solving differential equations. Okay?
Okay.
And these can get really, really tough. And it's not obvious. In fact, let's just go over that. I'm not sure I'm going to be able to make progress on that first one just because that's a special kind of differential equation.
Okay.
Just to alert you, notice that the x and the y are being multiplied here. So I can divide by y cubed and end up with an expression that I can integrate both sides. If it was something like this, can't do it. I could subtract y from both sides, so I'd have a minus y dy. Well, actually, I would have dy minus y. And I can certainly multiply both sides by dx, but that doesn't give me dxx. Because really I have dy over dx minus y equals x, and now I can't even get rid of the dx. In other words, when you have addition or subtraction taking place on the one side there, it's very difficult to separate the variables. There are a number of techniques for solving differential equations, and in college this is a full semester course.
Oh, wow.
On differential equations. It's a lot like integration. You know how there's like 7 or 8 techniques to integrate a function?
Yeah.
There's substitution, there's partial fractions, there's integration by parts. You've probably had all of these. There's integration by trig substitution, there's integration by infinite series. There's all these techniques. Each one's harder than the previous, harder to learn. Well, the easiest differential equations to solve are where you can separate the variables. One like that. Okay? And the only way you can, and it's not real clear why you can't integrate dy minus y. It's got to be dy times y. Then you could integrate it. Or dy divided by y. There is a special technique to handle this situation, but that's probably 2 hours worth of explaining just to explain that one. So the easy differential equations all follow your second one. They're all solved like that.
Okay.
If you have another easy one that you'd like to work on, we can do it. Or I can search through my book and see if I can find out something about this population one. These are...
No, I have another sort of easier one that we could do.
Let's do some that are more in line with... If you get if you get a question like that, you're only getting one of those on the test. Whereas you might get 4 or 5 easy ones because they don't take that long to do. So
this one's a little less easy, but here it is. It's dy over dx is equal to 2xy cubed sine of x squared and y of 0 equals -1.
Yeah, it shouldn't be any harder. We're gonna, is it sine squared of x or sine of x squared?
It's sine of x squared. The x squared is in parentheses.
Oh. But not the whole sine. In other words, it's like this.
No. Yes, that's correct.
Because this is definitely not the same as this.
Yeah, for sure.
Okay, they're very clearly different.
Yeah.
Okay. So we'll separate our variables. The only y over here is y cubed, so I'm going to end up with dy over y cubed. Over here, I'm going to end up with 2x sine of x squared dx. I can integrate that, right? Can you integrate that?
Yeah, it's y to the -2 over -2, right?
Yeah, the right side is y to the -2 over -2. That's the left side, rather. And what's the right side? How do I integrate something that looks like that?
Well, don't you have to do like the product rule?
Actually, no. There is no product rule for integration.
Right, it's U substitution, right?
U substitution, correct.
Okay.
What would I let U be?
This is where I always struggle. I never know what to make.
Well, it's tough when you're dealing with trig functions. Let's go over it. In fact, let's do these two problems right here. Hold on a moment. What you want when you're using U substitution is that sine of x squared is being multiplied by 2x, right? Well, that's the derivative of the inside. That's what you're always looking for. When you have a composite function, you're looking for the multiplier to be the derivative of the inside, and if it is, you can just use the power rule on this thing. Okay. But let's go through the U substitution part. What was I going to... Yeah, I can't remember my line of thought. But so we're going to let U not equal sine x, because that would not let us represent that properly. But if we let U equal x squared, now we're going to be in business. Okay. If this is the expression, U is sine of x, because then we would have U to the fifth.
Oh, okay. All right.
If the expression is this, then U has to be x to the fifth, because then we would have the sine of U. We can integrate either the sine of U or U to the fifth. But what we can't integrate is if I try to let U be sine of x here, I cannot rewrite that expression as U.
Okay.
You've got to be able to rewrite the expression as a function of U. Okay, well, if I let U equal x squared, I'm going to be able to do that, because now I'm going to be able to write that as the sine of U.
Okay.
Okay.
All right.
But the next step, whenever you're using U substitution, is to take the derivative of what you've let U equal to.
Right.
So du dx is equal to 2x, which makes du equal 2x dx. Now, if you look at this expression, I can turn that entire integral into an integral of U. Here's what I've got. I've got 2x sine of, instead of x squared, I'm going to write U. I still have a dx. Well, see that 2x and that dx?
Yeah.
That's equal to du. Doesn't cancel. It's replaceable by du.
Okay, I've never done it that way before.
Yeah, well, it saves a step. I mean, there's two ways to do this. You could actually solve for dx and then just substitute for dx. And in fact, that actually explains it a little bit better. Let's do it that way.
Okay, all right.
We're going to let dx equal du over 2x, just doing the algebra.
Right.
And now, when I go here, I've got, in place of dx, I'm substituting du over 2x.
And then the 2x's cancel,
and then the 2x's cancel. In other words, you always find the derivative of your u in the denominator. So for it to get canceled out, you need in the numerator the multiplier to be equal to that derivative. So those go away, and you end up with the integral of sine u du, which I can do. That's negative cosine u.
Right.
And now go back and resubstitute for u, so you end up, oh man, where did I? So you end up with minus cosine of x squared plus c on the right side. On the left side, we had 1 over minus y squared.
Okay.
And to solve the initial condition, we've got y of 0 equals minus 1, which means when x is 0, y is equal to minus 1. So we should be able to solve that for c pretty easily. If y of 0 equals minus 1, so when I put 0 in for x, my y needs to be minus 1. So minus 1 squared is 1, so I get minus 1 over there. I'm putting in 0 for x, that's 1. Cosine of 0 is 1, plus c, that tells me c is 0, which tells me that the entire solution is that. Again, I can get rid of those. Again, I can flip them so that I have y squared equals 1 over cosine of x squared. Well, 1 over cosine of x squared is secant of x squared.
So y equals secant x.
So y equals, no, the square root of this is not secant. Square root of that is that.
Oh, right, because it's only the x. Okay.
Because the x is being squared, it's not secant x times secant x. In other words, when I write sine squared of x, that means sine x times sine x.
Right. Okay.
When I write sine of x squared, it doesn't mean that. It means you're squaring the x and then taking the sine of it. So I can't take the square root of secant of x squared easily. So I've got to leave the answer like this. And that should be in other words, there would have been a plus c over there, but c was 0. So that should be your answer.
Yeah. Okay, cool.
And whether or not you turn that into secant, normally there's kind of a general rule that you don't leave trig functions in the denominator. I'm never gonna give an answer like that. It's kind of like leaving irrational numbers in the denominator. You don't do that. Okay, I'm always going to make that answer cosecant x.
All right.
And similar for what we just did there.
Okay.
All right. That should be a little helpful to you on solving differential equations. The only, I know we're only doing a half hour here, just wanted to bring up one last point.
Okay.
If I have this, I'm trying to solve that.
Okay.
This becomes natural log of y.
Right.
It becomes x cubed over 3 plus c.
Okay.
Now, how do you solve that for y? Because your goal is always to solve for y. What's that?
You multiply it by e, right?
You don't multiply it. You let this be the exponent. It's called exponentiation over e. So in other words, I can, if natural log of y equals that whole thing, then I can make e to the natural log of y equal e to that whole exponent.
Oh, okay.
And this gets a little tricky. On the left, that comes down to y. So we've solved for y. On the right, notice that I have the following, and this is where it's a little different. Right?
Yeah.
Well, let me erase some of this other stuff here. So y equals this,
Uh.
but that can be separated because when you're adding exponents, it's the same as multiplying. So that's the same as e to the x cubed over 3 times e to the c. In other words, if I said do that, this is what you would do. You would add the exponents, right?
Yeah.
So we're unadding them. And what happens is this e to the c is just a number, right?
Yeah.
Because e is a number. So e to the c is the same thing as a c. I can replace that whole thing by a c, and now the c goes in front like that. So the c becomes a multiplier, not an additioner. And specifically on this problem is where it comes up repeatedly, where you end up with the natural log of y on one side and something plus c on the other. This turns into this. And that's actually fairly critical because it matters a lot whether c is a multiplier or c is being added. It's not this plus c.
Cool.
Okay? So that's the only other hard one that you might come across, and I would expect you to come across that. So whenever you're looking at that, know you're going to have to do that process. Because the integral of that is always natural log of y, and then you always have to exponentiate both sides.
Okay.
Okay?
All right.
All right, Brent.
Yeah, this is good. Help me out.
You go. Good luck, and let me know if I can be further assistance.
Okay. Thank you.
You're welcome. Bye-bye.
Have a nice day.
You too.